Okay, so now we've looked at what the basic graph or the parent function of an exponential graph and a logarithmic graph look like. We're now going to do some transformations with those graphs. Before we do that, we need to actually have a quick review of all of our transformations from the second unit we did this year. So let's go through each one very quickly, one by one. If we have some function, and remember these transformations work for any type of function, even though we're going to, in this podcast, focus on exponentials and logs, it works for any function. If we have some function f of x, and then we add a constant to that function, it's translated vertically a units up. So it's moved a units up. And then similarly, if we subtract a number from the function, it's translated a units down. So that's quite easy. Remember, if it's outside of the function, it's always a vertical transformation. If it's inside the bracket with the x's, it's then a horizontal transformation. So for example, looking at this one, here we add a to the x before we perform whatever the function is. If it's plus a, when it's horizontal, it always behaves the opposite to what we think it should. So it's translated horizontally because it's in the brackets with the x, but it goes to the left. And then similarly, if we subtract a from the x, it's inside the bracket with the x, so it's translated horizontally, but this time it does opposite to what you think, and it moves to the right. Here we have the negative outside the function, and so that is reflected in the x-axis. It's like a vertical, it's flipping vertically, and so that's where it still follows the rule like up here. It's outside the function, so it's a vertical transformation. So it gets reflected in the x-axis. As opposed to if it's inside the function with the x, so the x is made negative, it's then reflected in the y-axis, which is like it's being flipped horizontally. And then our last two, if we multiply the function by a constant, call that k, the k is outside the function, so it's a vertical stretch, and it will be stretched by factor k. So if this is 2, it gets stretched by a factor of 2. As opposed to if that constant is inside the bracket with the x, it gets stretched horizontally by a factor of 1 over k. Let's try and fix that. So if again it was 2 on the outside, 2 inside with the x, let's see if I can just show that. So if this was a 2 here, then it would stretch horizontally by a factor of a half. So those should be fresh in your mind. You should know those from the second unit we did this year. Now we're going to put them into practice with our exponential and log functions. So here we've got our first example. We'll do it with an exponential function. And then the second example we'll look at with the log function. Okay, so we're starting with the parent function is 3 to the power of x. So it's given to you here. This graph is 3 to the power of x. Then we want to sketch the function of 3 to the minus x plus 1. So the first thing what we need to do is we need to decide, well, what are the transformations that are happening? So if we look at the plus 1, we'll start easy. The plus 1, it's outside the function, it's positive, so I know it's outside, so it's a vertical translation up 1 unit. Now remember, everything gets translated when it moves up or down. So that will include, because it's an exponential, that will include the asymptote. So vertical translation, 1 unit up. Then we have this negative. This negative is with the x. It's inside the function. So this is going to be a reflection because anything with negatives is a reflection. So it's reflected. Now we need to think. It's with the x. So it needs to be like a horizontal reflection. So it's actually going to go this way. This is horizontal. So it's going to get reflected in the y-axis. Okay, when you do these transformations, you should always start inside, start closest with the x and then perform anything that's outside the function. So in this case, the plus 1. So if we've got 3 to the minus x, basically the y-axis is going to be our mirror. So it's going to have the same shape to start with. We'll forget about the plus 1 to begin with. Same shape, and it's going to go up this way though, and then down this way because it's reflected in the y-axis. But then we also have this plus 1. So when it's just a reflection, the asymptote stays the same, the y-intercept will stay the same. It's just literally like a mirror, like this. So it's going to go this way. But we want to add the 1, so we need to move everything up 1. So now my y-intercept is going to be at 2. And remember, currently the asymptote is on the x-axis. And so that's also going to get moved up 1. So that's going to actually now be at 1. So this is where it's very important to draw the asymptote. You must draw the asymptote in as a broken line, so it's very obvious that that is the asymptote. So we just draw just a broken line here. There's our asymptote. And remember, this has been reflected, so it's got to go now this way, passing through the 2 as our intercept, our y-intercept. Now what I would also do is pick another point. You should always have 2 points. So your y-intercept's the easiest point to find. Pick another point just to get the steepness right. So pick a nice easy one. I would pick, for example, something like when x is, let's say when x is 1, we know here is the point 1, 3. Because here up here, the parent function was 3 to the power of x. So when x is 1, y is 3. So what happens is this point gets reflected over here, so it becomes the point minus 1, 3, but then it gets moved up 1. So it then becomes the point minus 1, 4. So we can write that one there. And then it's just a matter, remember, we just need to get the shape right now. So you're doing it up with a nice smooth curve. Try and do it as smooth as possible. Use a pencil. Now it should be a smooth curve, so you shouldn't use a ruler for drawing the curve part. Of course, use a ruler for the drawing the line there. And I know this is an asymptote, so it's going to get very close to it. And I know then on this side it's going to go on infinitely. And so there is my graph. Y equals 3 to the power of negative x plus 1. And on this end it goes on forever. So now it asks us, state the domain and range of y equals 3 to the negative x plus 1. So what we just drew. So when we have the graph, it makes it a lot easier to find the domain and range. So the domain is quite easy in this case because x can be positive, x can be negative, x can be 0, x can certainly be a fraction, decimal, so x can be anything. So it doesn't change when we do this transformation. It's still all real numbers for the domain. We can use any value of x. The range, however, is not going to be as many values because we can see, yes, it goes on forever in this direction. So in the in the positive y direction, it's going on forever and ever. But when we go in this direction, this is an asymptote, this broken line. This is, remember the line, y equals 1. And so you must always write the asymptote, the equation of the asymptote as an equation. That means it should have an equal sign. If you just write 1, that's not correct. It needs to be y equals 1. And so we know the whole idea of an asymptote is it gets closer and closer to the line but never touches it. So the smallest value that y will take on will be anything that's greater than 1. Remember, it doesn't touch it, so it won't be 1. But then it goes on infinitely in the positive y direction. So we know y has to be greater than 1. All right, let's try one with a log. So same idea. It doesn't actually change. It's just a different graph to begin with. That's all that's different. So let's get a different color this time. So we've start off with the graph y equals log x base 2. And remember the base, all it does, just like with the exponential, it just changes the steepness. So here is our parent function. That's the graph we're given here. We know with all basic parent functions here with log x base 2, base a, always has an x-intercept of 1, 0. always has the y-axis as an asymptote. Let's see what happens now. Let's start with this -2. This -2, it's inside the bracket with the x, so it's horizontal. And it's just, whenever it's plus or minus, it's always a translation. So it's a horizontal translation. And remember, when it's a horizontal translation, it always behaves opposite to what we think. So it's quite normal to think that that would move to the left, but it actually moves to the right. So it's a horizontal translation, 2 units right. So that's the first thing. So again, we need to be careful here, because of course we can take the y-intercept, the x-intercept, move that 2 units to the right. But the other thing we will need to move, remember the y-axis is an asymptote, so that will also need to move 2 units to the right. And we will start with that transformation because that's the inside. You try and start with the most inside translation. Then we have this negative. It's outside the function. So it's something that's happening vertically. And remember, anything with a negative that's being multiplied, obviously, multiplying by negative, it's a reflection. So reflected in, because it's outside the function, it's happening vertically. So it's reflected up and down this way. So this time the x-axis is going to be the mirror. So it's reflected in the x-axis. So we'll do that make that the second transformation. All right, let's just put some points on to help us begin with. So we need to move everything 2 units to the right. Let's start with the easy point. We'll start with the x-intercept. So it's currently at 1, so it's going to be at 3. Our asymptote is the y-axis. That has to move across. So that's, remember, x equals 0. We move it across 2. So now it's going to be x equals 2. Now the asymptote's not going to get affected by any sort of reflection. So we can draw that one in. Remember, of course, this should be done in pencil. This line should be drawn with a ruler. So this is now the line, x equals 2. We have our x-intercept at now 3, 0. So always clearly mark where the asymptotes are and the intercepts. Might be a good idea to take another point. So for example, let's see if we can take a point. Where's one that we can read off? Now you need to be careful when you're reading it off. Can we find one that's exact? It's a little bit hard to do, isn't it? This point here will not be exactly at 1, because I know if I substitute 10 in there, I wouldn't get 1. But we can take that point. It looks pretty close to it though, so we'll move that across 2 as well. Now, this point will get affected, of course, though, in the reflection. So everything has to, remember, your x-axis is now the mirror. So this is going to go down here, so it's probably going to be pretty close to -1. And remember, it's just a sketch, so we just want to get the shape right now that we've got the points right. So you've got 2 points. This point, the x-intercept, we've got our asymptote. So what has to happen? Everything gets flipped. So here, sorry, remember, it's being moved across, and instead of going down though, because it has to get reflected, it's got to go up. And then this part here is going to be, instead of above the x-axis, it's now going to be below the x-axis. So it's like an upside down log graph. So if I start by drawing this part and just try and draw it with as smooth a curve as possible, unlike mine. Okay, that's going to get really close to that line. And then here, this is going to be quite flat. You just do the best you can. But of course, it does go on forever and ever. It just takes a while to increase. It's going to be something. It's not actually a straight line there. It's just that it gets so close. So this is the graph. Y equals negative log base 2 of x minus 2. Okay, so it is a sketch, but you need to clearly show any important points, any important features like asymptotes and that sort of thing. All right, let's talk about domain and range of our new graph that we've just drawn. So for our domain, we are not using all of the x values, as we can clearly see from our graph. Here is our asymptote, x equals 2. We're not using anything less than 2. We're not using 2. Remember, it's an asymptote, so the graph only gets very, very close to it. But we're using all of the x values because this will go on forever and ever. We're using all of the x values bigger than 2. So our domain is x is greater than 2. Our range is a different story. Here, this goes on forever and ever. So these y values are going to get bigger and bigger and bigger and bigger. Here, these y values are actually going to get smaller in the negative direction. So we're using all of the y values. So y is an element of all real numbers. Notice these domain and ranges, what's happening is the opposite to what happens in the first example here. Here we said that x could be anything and y had a restriction. But if we look at this one, here x has a restriction and y could be anything. This is because they are inverses. It always swaps when they are inverses. Okay, so now you're going to try doing some curve sketching on your own. Good luck.